5-in-1 engine. The problem was simple and the solution was insane. In 1941, the United States Army needed an engine powerful enough to drive a 30-ton tank across any terrain the Second World War could produce. And it needed that engine immediately. There was no time to design something from scratch. Executive engineer Harry Wilson at Chrysler looked at the requirement, looked at what was available, and made a decision that no sane person would have made unless the alternative was losing a war. He took 5 standard Chrysler car engines, the same 6-cylinder units going into Plymouth sedans, and bolted them together around a common output shaft in a configuration that resembled a 5-pointed star viewed from the end. The result was the A57 Multibank. 30 cylinders, 5 carburetors, 5 distributors, all synchronized to produce 445 horsepower from what was essentially a parking lot of car engines arranged into one mechanical fever dream. It worked. It powered the M3A4 Lee and M4A4 Sherman tanks through North Africa and beyond. Mechanics who serviced it described the experience as maintaining 5 separate cars simultaneously in a space designed for one engine. The Army replaced it with a purpose-built engine as soon as one became available, not because the multibank failed, but because no mechanic should ever have to deal with 5 carburetor linkages in a tank. Before we go any further, if strange machines and forgotten engineering are your thing, hit subscribe and drop a like on this video right now. It genuinely helps this channel keep making videos like this one, and the engine coming up next might be the strangest one yet. Triangle engine. Most engines are designed around a crankshaft. The Napier Deltic was designed around 3 of them. Its cylinders are arranged in 3 banks forming an equilateral triangle, with a crankshaft running along each edge of that triangle, and each cylinder shared between 2 crankshafts, one at each end of the piston. The result is an opposed piston engine of extraordinary compactness and power density, producing 1,650 horsepower from an engine small enough to fit where a conventional engine of equivalent power could never go. Napier developed it in the early 1950s for fast naval patrol craft, where the combination of high power and compact dimensions was the difference between a vessel that could intercept and one that could not. The British Railways later adapted it for diesel locomotives, where the Deltic engine gave its name to an entire class of trains, the Class 55 Deltics, that became some of the most powerful diesel locomotives ever operated on British main lines, pulling express passenger services at speeds that humiliated the competition. The triangular cross-section that gives the Deltic its name is visible immediately when you look at one from the end, 3 crankshafts, 3 banks of cylinders, a geometry no other production engine has replicated before or since. Duke Axial engine. The Duke Axial engine looks like something an engineer designed after deciding that the conventional engine layout was simply not strange enough. Where every standard engine has cylinders pointing away from the crankshaft at various angles, the Duke Axial arranges its 5 cylinders in a circle around the output shaft, all pointing in the same direction as that shaft, parallel to it rather than perpendicular. The pistons drive a swash plate, a disc mounted at an angle to the shaft that converts the reciprocating motion of the pistons into the rotary motion of the output shaft, the same principle used in hydraulic pumps and aircraft propeller pitch controls. The result is an engine shaped like a barrel or a drum, extraordinarily compact for its displacement, with no side loads on the pistons because they travel parallel to the shaft rather than at angles to it. The Duke engine produces power strokes from all 5 cylinders in rapid succession as they fire around the circle, creating a smoothness of power delivery that conventional engines cannot match at equivalent cylinder counts. It has been proposed for aircraft, marine, and generator applications, and it runs. What it has never achieved is production at commercial scale, not because the engineering is wrong, but because the manufacturing processes required to build the swash plate mechanism to the required tolerances add costs that conventional engine architecture does not. Spinning engine. The Adams-Farwell rotary engine solved a cooling problem by creating a problem that nobody had previously considered needed solving. Conventional air-cooled engines of the early 20th century struggled to cool their cylinders adequately because the cylinders sat stationary in the airflow. The Adams-Farwell solution was to spin the cylinders, to mount the entire engine block, all 5 cylinders, on a rotating assembly that turned around a fixed crankshaft, using centrifugal force to throw heat away from the cylinder walls and the spinning mass itself to draw cooling air across every surface simultaneously. It worked as a cooling solution. It also created a gyroscopic effect of considerable force that made the vehicle it was installed in, an early American automobile, handle in ways that its driver had to learn through experience rather than intuition. Turning the steering wheel created forces that the spinning engine mass amplified in unexpected directions. The Adams-Farwell was used in a small number of early automobiles around the turn of the 20th century and achieved a modest following among enthusiasts who considered its unusual handling characteristics part of its character rather than a flaw. The rotary engine concept it pioneered, the engine block spinning rather than the crankshaft, would later appear in the aircraft engines of the First World War, scaled up to far greater power and far more consequential gyroscopic effects. The knocker. The Commer TS3 earned its nickname from the sound it made, a distinctive mechanical knocking that mechanics learned to identify from a distance and that set it apart audibly from every other diesel engine operating on British roads in the 1950s and 1960s. The source of that sound was its configuration, an opposed piston engine with 3 horizontal cylinders, each containing 2 pistons moving toward and away from each other with no cylinder head between them, connected by a system of long rocker arms to a single crankshaft below. The rocker arms are the visual signature of the knocker. Long curved mechanical levers that convert the outward motion of the upper pistons into the downward motion required by the crankshaft below. And it is those rocker arms working under load that produce the characteristic sound that gave the engine its name. It was used in Commer trucks and buses across Britain for over a decade, and mechanics who worked on it regularly described a love-hate relationship with its unusual geometry. Difficult to work on in ways that conventional engines were not, but producing a power output and fuel efficiency that its contemporaries struggled to match. The knocker is the engine that sounds wrong, looks wrong, and worked well enough to stay in production for years, despite both of those things. Napier Sabre. The Napier Sabre H24 is what happens when an engineer decides that 12 cylinders are not enough and 24 are the minimum acceptable starting point. Its cylinders are arranged in an H configuration, 2 flat 12 engines stacked vertically and geared together at the center, producing 24 cylinders in 4 banks of 6, all contributing to a single output shaft. At full power, the late-model Sabre produced 3,500 horsepower from an engine compact enough to fit in a single-engine fighter aircraft. The Hawker Typhoon and Tempest that it powered were among the most capable ground attack aircraft of the Second World War. The engineering required to make 24 cylinders work reliably in a fighter aircraft was, in the early 1940s, substantially beyond what British manufacturing could consistently deliver. Problems with the sleeve valves caused engines to cease in service, and reliability was so poor in the Typhoon's early months that the aircraft nearly had its program canceled entirely before the manufacturing issues were resolved. The Sabre was notoriously difficult to maintain, temperamental to start, and sensitive to the quality of the mechanics assigned to service it to a degree that no other engine in service demanded. By the end of the war, the Sabre-powered Tempest was regarded as one of the finest piston engine aircraft in service. The path to that reputation ran through years of mechanical frustration that the 24 cylinders made inevitable. Tesla turbine. Nikola Tesla patented the Tesla turbine in 1913, and it has fascinated engineers ever since, while never quite achieving the commercial success he imagined for it. Where every conventional turbine uses shaped blades to extract energy from a moving fluid by deflecting it, the Tesla turbine uses no blades at all. It consists of a series of smooth parallel metal discs mounted on a shaft with small gaps between them. Fluid, steam, gas, water, or air enters at the outer edge of the disc stack and spirals inward toward the center, transferring energy to the discs through viscosity and adhesion rather than through impact and deflection. The discs spin, the shaft turns, and the fluid exits at the center. The elegance of the concept is undeniable. No blade profiles to machine, no complex aerodynamic geometry, no turbine blades to crack or fatigue. Tesla believed it would replace every existing turbine design. It did not, primarily because the boundary layer effect that makes it work also limits its efficiency at the scales where conventional turbines operate most effectively. It performs best at small scales and with specific fluids, and it has found applications in pumping, flow metering, and specialist industrial processes where those characteristics are advantages. The Tesla turbine is the engine that works exactly as its inventor intended and never quite became what he promised. Pulsejet. The Pulsejet is the simplest jet engine ever built and the most violent. It has one moving part, a set of inlet valves, and in some configurations, it has no moving parts at all. Fuel and air enter the combustion chamber. The mixture ignites. The explosion drives exhaust out the rear. The pressure drop opens the inlet valves. Fresh air and fuel enter. The cycle repeats. The V1 Flying Bomb's Pulsejet fired at approximately 45 times per second, a frequency so low and so loud that witnesses on the ground could hear the individual pulses as a continuous buzzing drone, which is why Londoners called it the buzz bomb. At higher frequencies, smaller pulse jets can reach 250 pulses per second, producing a sound that witnesses consistently describe as somewhere between a chainsaw and artillery fire. The Germans used it to power the V1, the weapon they called the Vergeltungswaffe, the vengeance weapon that they launched against Britain in 1944, and the distinctive sound of its pulse-jet engine became one of the most feared sounds of the Second World War. Londoners learned that the sound of a V1 engine cutting out meant the bomb was now diving toward them in silence. The pulse-jet that powered it cost almost nothing to manufacture compared to a conventional aircraft engine, could be built in factories with basic tooling, and required no specialist knowledge to assemble. It was the democratization of jet propulsion applied to a weapon, the principle that the most destructive technology is often the simplest, and that simplicity is the hardest thing to defend against. Triangle rotor. Felix Wankel spent years trying to build an engine without pistons, and on the 1st of February 1957, the first prototype ran at NSU's research facility in Germany. The Wankel rotary engine, named after its inventor, replaces the reciprocating pistons of a conventional engine with a single triangular rotor that spins eccentrically inside an oval housing, tracing a path that simultaneously creates intake, compression, combustion, and exhaust in different parts of the housing as it rotates. The elegance is extraordinary. No pistons moving up and down, no valves opening and closing, no crankshaft converting reciprocating motion into rotation, just a rotor spinning continuously in one direction, producing 3 power strokes per revolution, rather than the one that a single conventional piston delivers per 2 revolutions. The Wankel produces more power for its size and weight than almost any comparable piston engine, and runs with a smoothness that no reciprocating engine can match at equivalent power output. Mazda adopted it for the RX-7 and RX-8 sports cars, where its compact dimensions and high revving character made it the defining engine of a 2-decade performance car legacy. The engine's weakness is fuel consumption and sealing. The apex seals that maintain compression between the rotor and housing wear in ways that conventional piston rings do not, and the engine burns oil as part of its normal operation in a way that would indicate catastrophic failure in any other engine. Mazda discontinued it in 2012 when it failed to meet modern emission standards, and reintroduced a version of it in 2023 as a range extender for the MX-30 electric vehicle, the engine that abandoned pistons entirely, returning not as a performance statement, but as a quiet generator keeping a battery charged. Felix Wankel would have had complicated feelings about that. 9 engines, 9 engineers who refuse to accept that a piston has to go up and down. Subscribe if you want the next batch of machines nobody should have built, and let me know in the comments which one of these you'd actually want to hear running.